Yeah, I appreciate the opportunity to be here today. I've really enjoyed all of my activities in Houston. And I think it's interesting, I was visiting today with the, here it is, near final. I'm not saying it's done, just a near final, okay? I was visiting down the University of Houston today because I've known Paul for a really long time. And I will say that when I first came from industry to the University of Texas, the first thing I did was I, of course, stopped across the hall, or actually they were on a different, like, couple blocks away by then, and I wanted to talk to all my friends in the Institute for Geophysics, because I did a lot of geophysical interpretation and data and stuff, and so I was like, oh, let's collaborate on something with them, and I have to admit, most of them were like extremely hesitant to collaborate, because they did big projects with NSF, and they did big projects with International Ocean Drilling Program, and some of the comments were like, oh my God, if we work with them, we'll never work with the NSF again, you know. And I'm like, well, Paul jumped right in with both feet, and so you see that. So much to his credit. And so for many years we ran a consortium called Deep Marine Depositional Margins, DM squared, because I thought, then it sounds quantitative, it's got a square on it. So so I've known Paul for a very long time. But the last time I gave a talk at the University of Houston, there were 6 professors in the department, I remember. And so it was really a pleasure to go today and talk with Julia's group, and talk with Rob, and talk with Paul's group and stuff, and the Indian Ocean guy, or the India teams and stuff, and see everything that was going on and what was being done. So just a lot of really good students. And so I think that I know everyone worries about it, but I really think that your young scientists are healthy, and they're interested, and they're enthused about what's going on. So one of the things I'd like to talk to you about today is some of that enthusiasm, and what enthused me when I first got into this. And so what I want to talk to you a little bit about today is, the title is very ancient. It's Seismic Geomorphology of Ancient Earthscapes, Strengthening Our Perspective of Deep Time and Clarifying Our Role in the World's Future. So I was clearly drinking a scotch the night I put that together. And I was like, we should talk about clarifying our role in the world's future. And so, but I want to thank several of you. Liza, as I said, is a University of Houston graduate. Dr. Cardona is also here. He's one of my graduate students. Enri Schombing is a person who's contributed to this. Rob Galthorpe, who's a close friend of mine, looks at rift basins. He Chen, who also contributed a lot of this. But TGS, CGG, Woodside Energy, BHP, Staatzel, all of these, the Trinidad Ministry of Energy and Energy Industries, there is probably not a company in this room that hasn't contributed data, as Paul was saying, contributed data to the research and to the education program that we have. I was in Amoco for 5 years and 13 days, and then I moved and went to the University of Houston, the University of Texas, to the Bureau of Economic Geology, where I was there for about 18 and a half years. And I, of course, in 2015, I moved to Colorado School of Mines to take the Robert Weimer Endowed Chair, which was an amazing opportunity. I was there when Bob was still alive. We had lunch several times. He's a great guy. But the opportunity to use that type of data to build the type of images and things that we've been able to build has just given me a completely different perspective on my science and my place in the historical evolution of the world, right? And so what I want to do today is just talk to you a little bit about this. We are fascinated with vistas. We are fascinated with images. We are fascinated with vistas like this. We are fascinated with maps, our ability. We want to be able to climb to the highest places, to look at what's the deepest point on the earth, what's the highest point on the earth, what's the largest river, what's the biggest sand dune we can find, right? And so we're fascinated with things like that. We've always been fascinated with ideas like that. The landscapes and seascapes that we see in the world form the foundation on which all sediment accumulates, and where tectonics modify the earth, and then sedimentation and things occur in evolution on other planets. This is an image of Oliver Lippincott looking out over the vista, which is the rim of the Grand Canyon in about 1900. And so this was apparently like the first time a car had ever driven to the Grand Canyon. Of course, now we know it's a little out of control, right? If you've ever been back, there's more going on there than Oliver Lippincott would ever have imagined when he drove his steam-powered Toledo down there. But it's this type of thing that, you know, keeps us coming back to look at these vistas of the Earth and different planets and stuff. For, you know, geologists, we tend to map the Earth's landscapes and seascapes. We want to understand how they've changed and how they've evolved over time. This is probably an image of the very first map. This was found, and it's about the size of your iPhone, which ironically, it's about the size of your iPhone now, which is what we've all come back to. But this was created, you know, 2,500 years ago. We've been mapping things for this long, and it's really meant to represent the Euphrates River, and it's surrounded by an area the text suggests is called the Bitter River, which is probably the ocean. It's a salty river, salty area. And then it actually flows into an area which is kind of a swampy outflow area, like this. And you may notice that it actually has several sort of triangular-looking mountain fronts all the way around it, right? And this is that area, the fertile areas of the Euphrates River. And this was not a map that was meant for anyone to sort of walk to the swamp and then walk to the Euphrates River and then walk. It was not for navigation. It was to create a sense of perspective of where the holder was holding, you know, this very small map sort of sat in the world and where they were relative to the ocean, relative to the Euphrates, relative to the swamps. And so, you know, this is the same thing we search for when we look at vistas and we look out over the Earth and out over different planets and stuff, right? So maps, as we've created them, we've started with, you know, things that sort of look like this, right? And then with one of the things I want to do in this talk is emphasize the importance of seismic data and how it's changed our perspective of where we live and also where we work. So, you know, once we began to get seismic data, we were able to add a different dimension to this type of thing. We were able to add a third dimension to this. And really, we add a fourth dimension when we began to look at landscapes over time, right? And so we now have a four-dimensional aspect of things that we didn't have before. And, you know, maps are not made alike. And as we've evolved computers, we've been able to do more and more and more with, you know, as, you know, we say, you know, 5 terabytes of data or something, you know. It's like we can do more with the data we have. What we're looking at today are things like this, right? And I think this is an amazing image. I borrowed it from Israel, Polonia, and he has a really great, what is it? It's not a Twitter site, it's an Instagram site. He has a really great Instagram site, and he puts together a lot of images and stuff. And so he very graciously, you know, I asked him if it was okay to borrow this image, because this is an image of the early Mesozoic Paleo landscape of the North Sea. It's an area of the North Sea. And so, you know, now you can really begin to see the basins, and you can begin to see, this is called the Pancake Basin, and here sediments are moving through here. You've got a lot of canyons and stuff evolving. You've got a lot of sediment pathways. I mean, you could imagine standing and looking out over this landscape, you know, if you were a dinosaur, I guess. And this is what the early Mesozoic looked like. Geology, as it exists, provides a lens through which we can witness time in a way that transcends the limits of our human experience. We can fathom deep time. Fathoming deep time is arguably geology's single greatest contribution to humanity. And this is important because there are no other real sciences out there that can fathom deep time the way geologists can. And the inability to fathom the depth of the Earth's history and the future of the Earth sometimes lead to decision-making processes that are uninformed, right? But geophysics especially has offered us an opportunity to view the time through a lens that we can witness the way the Earth evolves, and it transcends our human experience, right? So we have a very finite lifetime, but we can look at the Earth's evolution over millions of years and understand it, right? This is from a book that I had read recently called Timefulness. And it's a 2018 book, but it talks a lot about time and and the importance of geologists being able to recognize and input into that question. The other thing that evolved that enabled us to move forward really in looking at landscapes and stuff was the development of what I call the MEG. It was the birth of the Mega Survey, and it changed the face of mapping the Earthscapes in seismic data, right? Let me make sure I'm displaying this right. It's kind of interesting. Yeah. And so it enabled us to do things like this, to build maps that were so large in scale that we could actually view what it was like to live in areas of the North Sea over long periods of time. And by using these type of images, we're able to come in and understand paleo landscapes and the way that humans and populations move in and around paleo landscapes. How did they migrate from areas of Europe over to areas of the UK? Well, you don't have to imagine too much with a system like this. It lays bare the tributaries and the river systems and the morphology that those cultures were moving in and around as they were migrating from areas of Europe over to the UK or over to areas of Norway. And so this is empowered by these mega-merge surveys. And this is one of the bigger ones up in the North Sea. I think it's about almost 140,000 square kilometers of data. And it's just made by merging together, hundreds of surveys together into a landscape, an evolving landscape. And so I want to use these merged surveys and these mega surveys just to show you a few of the landscapes that I've worked with over time and how meaningful it's been to me to be able to see the Earth this way. Because the idea is that we will use these images to make predictions about how is the Earth going to evolve, how are human populations going to move and migrate in response to the evolution of these landscapes and seascapes, right? So the idea is to use them in a predictive fashion. And we have a responsibility as geoscientists, because of our ability to see deep time, we have a responsibility to use that power to understand the past and predict the future, right? This is an image of a woman, and this is sort of what was predicted to be an automatic vacuum cleaner back in the late 1800s, right? Now, I'm not saying that our predictions are always totally correct, right? Because oftentimes, we sometimes have the right idea, but the execution is a little different than what we anticipated, right? But what's important is that it stimulates ideas, right? And how we build stuff. And so we do have automatic vacuum cleaners today, and the cats ride around on top of them, so I don't have a cat. So let's look a little bit at some of these. This is a North Sea Rift Basin landscape and seascape. It allows us to, this is a three-dimensional image of the, I believe this is the Cretaceous, the top of the Brent. So this is a late Cretaceous unconformity at the top of Brent, and this is over 100,000 square kilometers, and it's about 50 kilometers square on the side. But it allows us to ask questions like, how do the submarine processes interact with complex topography? Where's the major sediment sources for the area, right? What does the geomorphology of the landscapes and seascapes look like? How do populations interact with such type of earthscapes, right? And so if we look at these type of things, we can see these. I mean, this orange surface is actually, the orange surface down in here is this surface of evolution up in here. And so being able to see that type of surface from 2D now evolved into a three-dimensional image is just stunningly powerful. It allows us to drape over or underlie the stratigraphy, the subcropping stratigraphy of the unconformity. And so when the unconformity was forming, this is what the topographic map looked like, right? And so you've got Lund Formation, you've got Dunlin Formation, you've got Brent Group Formation back in here, and then you can begin to assess, what's the structural fabric and how is the underlying subcrop influencing the structural fabric of things, right? So this is just one image in the North Sea that you can generate from this, and this is generated by was my master's student. Now I'm on his PhD committee, and he's working with Rob Galthorpe to look at, in this Deep Basin Rifts project, looking at these rifted margins, and he's going in and I'm asking him to look, what are the feeder systems, map the canyons, look at the structural controls on the canyons, look at the footwall faults, look at the type of blocks that are falling off the margins of the rift. So this is real-time geomorphology that's evolving. And this is important because we generate very complex geometries in these surfaces. If you just have a flat map, sometimes you don't appreciate the complexity of the topography. But the topography itself is just a piece of the puzzle. What's important is not just the topographic characteristics and the accommodation in the setting, but also how do gravity flows interact with that topography. And that's when you get into things like what I call accommodation scapes. The accommodation is just the space for the sediment, but it's the landscape and it's how the gravity flows interact with the landscape that ultimately result in how you fill that accommodation stuff. This is just an older image of a physical model, but I want you to look at this. Look at how the gravity flow, maybe the gravity flow coming. It's thinking about coming in. It's thinking about, oh, there it is. Look at how the gravity flows. Look how it's outrunning itself over here. It's going to come around here and run into itself. It's like a carnival of clowns, right? And there, it's going to gap over these structures. So if you have a structure, if you have something like this, and you really want to understand how these gravity flows interact with a structure like this, you're going to have to understand how gravity flows move in and around topography. And to start with, you're going to have detailed maps of the topography in order to understand this, right? And so just like you're looking for people to map seafloor stuff, we're also looking for people to map these ancient seafloors. These are ancient landscapes and seafloors. Once you have that information, I'm going to shift over to Australia now, to those rift basins. This was a very nice piece of work that was done by He Chen, a student of mine, and Rob Galthorpe and myself, where we took the drainage systems of those rift basins, and we began to calculate what was the capacity and what were the sediment budgets like along these rift basin margins. So we could come in and map the topography up in here. And then this is the deep rift part. This is the Lewis Trough down in here. And there are actually 6 major sediment basins in here. And not only could we map the drainages, but we could also map the fans that were being deposited along these drainages. And so this meant that we had the sediment in capacity and we had the sediment that was being deposited capacity. And by doing that, we could take a basin such as the Perseus Basin. We could map the watershed boundaries that are represented by these yellow lines. We could map the size of the watershed and the catchment length, and we could even come in and map the shape of the watershed. And if we had those elements, we could actually map the capacity of the watershed to shed sediment into the rift margin. And by having that capacity, we could compare that with the size of the fans that were down at the base or the footwall of the rift margin. And in doing that, we found 2 classes of drainages in here, right? One of these classes looked like the fans were undersized for the size of the catchment. And the other class looked like the fans were either right-sized or larger than they should be for the catchments. And so what was happening ultimately was sediments were being picked up from one part of the marine basin and shunted into this other class of fans. So it was outsizing or outgrowing the fans, and then the other fans were too small. But we could only figure that out by being able to map the paleotopography and then calculate the size of what the basins were capable of doing, right? And so then it leads to an understanding of process. This happens to be an image from the Gulf of Corinth. This happens a lot. We call this toe trimming, where deep currents are moving up and down the rift, and they pick up sediment from one area, they tow trim the fans, and they redistribute the sediment into fans in the downstream direction. This happens in the Gulf of Corinth. Rob runs a great field trip to the Gulf of Corinth, if you ever get a chance to go. But it's only by mapping the landscapes that we can see and we can begin to calculate the processes active in the landscape. So if we shift to a different type of basin, this is an area that Paul and myself and various people have been working for decades. This is actually an image that was generated by one of Paul's postdocs. Still using your stuff, Paul? He's like, because you're not able to calculate it yourself. I hear you. Haters gonna hate. So this area that I want you to look at is right down in here. It's a very interesting area. It's an area where rivers and currents and continents just collide. The 8th largest delta in the world is the Orinoco. The Guyana current sweeping up through here is one of the strongest currents in the world. And of course, the Caribbean plate is moving obliquely past the South Atlantic or South American plate here, and they're obliquely colliding in here. So there's a lot going on in here. This is something that Leiser's dealing with. Leiser figured it all out. He's got a paper published in the Interpretation Journal here in November on some of this. So I want to show you some of his stuff. If we look at this area, it's just northwest of the Guyana-Suriname margin up in here. Here's a good seismic line across the deep part of the basin. We were able to toggle together not 140,000 square kilometers, but a darn good piece of acreage, probably 60,000 square kilometers in here. And so we had data from the eastern shelf of Trinidad, we had data from the upper slope of Trinidad, and we had data from the eastern lower slope of Trinidad. And this is where I've been working down in Trinidad for, gosh, I don't know, 30 years or something. And so good portion due to people like Eric Williams, who's very supportive of academics and that we were doing at the University of Texas. And so they were always very supportive in giving data and supporting stuff. And so if we come down through here, this was our first attempt. And I tell you, when I saw this image, and this is an upper slope sediment pathway in the late Pleistocene, it brought tears to my eyes. Because for the first time, I could fly through the seafloor like I was in a little submarine, you know, with an experience like I had never had before that was enabled by the computing software that we had, right? And so I thought this was the bee's knees, man. I thought this was great. There were various, I don't know if you can see my pointer. There were various major pathways for sedimentation through here. They were coming off the shelf. It was being shed off the shelf in this direction. These holes are actually mud volcanoes in here. And it was great. And then we got more data. And we got data that attached to the end of this from the Ministry of Energy and Energy Industries, the courtesy of BHP, or Woodside, the company formerly known as BHP. It's now known as Woodside. And Leiser created something amazing. So this is going to take you from the easternmost edge of the basin all the way up to the western shelf that's feeding the basin. And what you're looking at, if I can get it to run, maybe it'll run, maybe it won't. What you're looking at is the mud mountains of offshore Trinidad. How high are these, Leiser? Come on, man. You're messing up my timing.
A couple 500,000 feet.
Yeah. So you gotta go through this thing. Start it again because Leiser messed up my time. So these are the mud mountains that sit up in here, okay? And in these mud mountains, you got these individual, you know, all these individual big mud volcanoes. These are all mud volcanoes. These are masses. And right next to this levied channel system, we have this, which is an unlevied channel system with slumps on the side and with no apparent levees on it. And it's sitting right next to one of the biggest levied channel systems that I've ever seen. It's weaving in and out between these individual mud volcanoes, some 250, 300 meters high. And it's coming up through here. Here's all these individual mud volcanoes on the seafloor. Some are collapsed mud volcanoes. And now it's going to come up through here, and it's going to source into the shelf up here. All right? And I could look at this over and over again, and I do. I often set and just put it on rewind. And yeah. And so this is, now we're coming up into the shelf where a lot of the fields are, a lot of the oil and gas fields are. And so this was an amazing thing for me to see, was this enormous mountain of mud that was sitting off here, these levied channel systems, big levied channel systems sitting in here, right next to these channel systems that are completely unlevied. I have no idea why this is happening. Normally, at a time period in the basin, you have big sediment supplies coming off of the basin and you're building big levees. But in this case, you have two completely different types of channels sitting within 1,000 meters of one another, and they're evolving completely differently. You have the mud volcanoes, which I think are fascinating, and in some cases they have these little bright, dots on top of them, and those are little methanogenic communities that are sitting up there and chewing on the methane, and carbonate communities that are living. You have these isolated mud volcanoes sitting out in here, and then you come up into the shelf. There's actually a collection of chondrites that are sitting in here, little chondrite sediment waves that are coming off the shelf, and then finally up into the rest of the shelf. And so, those type of things enable you to get passionately, sort of romantically engaged in the seafloor, right? And so when you say you have problems getting students to map the seafloor, I'm like, that's crazy. Because who wouldn't want to map something like this and fly through the seafloor, look at this stuff, right? This is from Leiser's paper. This is the outboard data. I used to think that all of this stuff stopped right in here, but now we realize that it just keeps going. Here's the mountains of mud in here, the individual levee channels, the incised sort of giant sort of canyon feeder systems in here, and sitting right out here in the middle of it, there are two productive wells that have, well, I'll say productive, but they have 450 BCF of gas proven in them, right? And so there's called Victoria and the Concepcion, I think. And so, one of the questions that we have is like, how are these big there's enormous mass failures coming off of this basin. It's like, how is that influencing the maturity and the development of these prospects and stuff? But these type of seascapes are just romantically fascinating to me. You've got attached mass failures, you've got detached mass failures, you've got the shelf edge setting up in here. What? Oh, sorry. Thank you. Let's see. You've got attached mass failures, you've got headscarps and mass failures up in here, shelf edge setting up in here, you've got isolated mud features, detached mass failures and canyons, dogs and cats sleeping together. It's like everything going on in this one image, right? So this is you could spend an entire master's thesis on this, but a PhD requires 2 more papers, so I'm just saying. So one of the things that Leiser's doing is he's jumping into looking now, we're beginning to get from companies multiple stacks of data, as we're realizing that one merged stack is not enough. So what are the nears? What do the fars show? We can extract root mean squared amplitudes, we can extract variance, we can extract something called chaos that I can't figure out what it is. And look at all of those attributes for an interpretation of what's going on, not just on the modern seafloor, but then the 4th dimension is going down through time to look at all these things. So the last type of system that I want to show you guys tonight is something that I was desperately like, is there anybody in here from TGS? Well, thank God for that. So, no, I was actually in my hotel room emailing these guys from TGS last week, asking them for permission to use some of these images that I'm going to show you. So these are kind of hot off the press. They've not been shown by anyone. They're very nice to give me permissions. So one of the more difficult landscapes to try to get a handle on in geophysical data and seismic data are shoreline and paralic seascapes and landscapes, because they're just so complex, right? And you have a lot of dunes, you have mud flats, tidal flats, you have sand shoals, you have barrier islands, you have all this complexity going on, and you're trying to image that in seismic data, often things that are, you know, a couple of meters in resolution. But it's important to try to understand these systems because as Paul was showing, you know, there's a maturity of hydrocarbons happening, for example, off in the Suriname shelf and the Guyana shelf, but the deal is it's all going up to the south. And so you need to be able to de-risk these type of systems to understand seal in your systems, right? These do work. This is an example of some you may know called the Cotton Valley. The Cotton Valley sits out there and it actually produces, it does seal in the sub-dip direction, right? And you've got a lot of hydrocarbons sitting out here, shore face and lagoonal sands and stuff being sourced from the marine shales. And so the Cotton Valley is one, but you may recognize this one. This is the Pica Field, Pica Field. Everyone in Australia calls it the Pica Field, but I call it the Pica Field. And so the pica was discovered a couple of years ago by some guys who claimed it was the largest thing in the world. I should always do that when you're trying to sell something. And so it's sitting up on the north slope up in here. It's a lower Cretaceous play. Its average porosity is 20%. It's got lots of oil in it. It's got a ton of oil in it, right? But if you look at it, here it is. And you know, it's these cliniforms of the Denusic, right? And then they come up into these top sets. And so really what they're playing are these top set plays, right? And they're playing these individual cycles in here in these top set plays, parasequences, these top set plays. But what you really have to do in here with this stuff is you can see why you've got to de-risk that seal. And that's where the paralic, the top sets and the paralic stuff are coming in. And let me tell you, they work here. They also work in the West Siberia Basin. So these are pure stratigraphic traps. And in order to de-risk these pure stratigraphic traps, you've got to have good seismic data. Because I'll tell you off in Suriname, there's very few wells off in the offshore area. And so you got to do this with seismic data. And so I had some colleagues at Staatselie. They were amazingly good at what they did. I was really pleased with these guys, younger people who were working on Staatselie. And there were multiple plays that we sort of looked at out in here. But this is the area that Paul was showing you out in here in terms of the maturity maps that he had built. This is the play fairway in here. And we're going to look at some data back in here. This was a beautiful data set. So I just took this off the TGS website. I've got another couple of images, but this is kind of what the data looks like. And in that area, and you can see these cliniforms coming out through here. And you can see this motley mess in here. I'll show that to you. But what this was there were a series of prograding shelf systems out here. And at first, whenever they said, oh, well, I think a good analog is probably the North Slope of Alaska, I'm like, well, who wouldn't, you know? It's like a huge, massive like play system. And then I actually scaled this down one day, and I was like, holy heck, you know? It is the scale of the North Slope of Alaska. It just depends on how you display it, right? And so if we look at some of this in here, there's actually the mother of all like mass failure surfaces in here. And that's a whole different beast in terms of play opportunities and seal and risk and stuff. And I was feeding something called the Lisa in the offshore. You may have heard of it. And the waves, the currents were sweeping these sands into these massive barrier island systems up in here. But in order for them to be productive, you have to prove the up-dip seal. And this seismic data allows you to generate the landscape views and images that you need to prove the up-dip seal. And so, a couple of notes just to wrap this up, is that the way we're able to image landscapes and seascapes today, not just on the modern seafloor, but in the ancient, it just dwarfs anything we've been able to do in the past. I can't imagine how it could get better unless we could physically put you on this surface and allow you to ride your mountain bike up and down it, right? And so today, geologists are using these type of images to build their understanding of deep time. And it's arguably the greatest single contribution to humanity that we can make as geologists, right? There is no other science that's able to fathom deep time the way we are, or look at time the way we are. Most of the world are short-term thinkers, right? We give bonuses, annual bonuses. We hire people, rehire people, or re-elect people sometimes not. We re-elect them on a 4-year cycle or a 2-year cycle. So we tend to be a short-term thinker type of society. That's what we've evolved into. And if there are long-term thinkers that exist, they kind of scare us, you know? It's like, he's kind of scary sometimes. But he's a long-term thinker, 20 years in the future. And a lot of times we don't reward that type of thing, right? But the reality is we need both. One of the problems that exists when you're a short-term thinker is you develop something called what I call survival deniability. It's like there's a temporality thinking where, well, we're making computers in 1960, but I mean, who could imagine, we're going to have a nuclear war with Cuba, so we probably won't survive into the year 2000. So you get to the year 2001 and all your computer clocks don't work because there was a temporality thinking at time, right? But as geologists, we know that we do ourselves a disservice when we build something like this, right? 4.6 billion years in 1 hour, right? And we go through all this stuff and we show kids this, and it's like all of a sudden 59.99 seconds and the first modern man appears. Well, we've only got 1/10 of a second to exist. And so we're probably going to disappear, right? And so this type of temporality of thinking causes what we've got today, which is a bunch of students that see no reason to go into geosciences. They see no reason really to get a job or get an education beyond, a kindergarten education because, well, they're clearly not going to survive for the next 30 years because global warming is going to kill all of them, right? I mean, I've talked to kids and they've said that, They've said, well, the world's going to an end anyway, so what's the point, right? So that type of survival deniability doesn't serve any of us very well. And so we've got to stop thinking that way, and we are the best culture and the best people to keep us from thinking that way because geology provides a lens through which we can witness time in ways that transcend the limits of our human experience. Now we're moving into other planets, and you talk about vistas. Amazing vistas. This is the rover Curiosity gazing out over Mount Sharp, Mars, right? This allows us as geologists to recognize that there's a deep time in these rocks that other people can't really see. They don't really see the deep time. It's the thing that causes me to look at something like this and say, oh, well, that's a delta. And other people to say, well, maybe it's a alluvial fan, And so we have the ability to go and interpret and map things like the Everest Fault Delta and things and understand the evolution of planets the way we've not been able to understand them. So just a few summary comments. We have a responsibility as scientists to use our insights into the depth of Earth's history to inform decision makers for the future. We have the ability to see the changes that are coming in energy and get in front of those changes. So we can't let the ballasts weigh us down, right? We need to move towards where we know energy is going. Stop wailing and carrying on about how high carbon energy is going away. It's like, well, so did coal fields, so did riding mules to town, to school, I guess, for some people. Geophysical acquisition of data has given a great gift to the world, and we need to recognize and acknowledge that contribution. Use your observations to interpret process. I see a lot of people making observations, but you can go farther. Interpret the processes. There's not enough scientists with using the full value of the seismic data. And finally, we need to find ways to encourage longer-term thinking and to recognize that we're going to be around for thousands of years in the future, and we need to plan for that. So, with that, I thank you for your time. I need you to go out to your seismic data and look for more vistas and do more calculations. So, thanks you guys, I appreciate it.
So you're willing to take a few questions?
I'm willing to take a few questions. So Doug's interested in knowing, is the industry pursuing more strat traps these days? And I would say, maybe. It's because, you know, Liza's a strat trap. It's a pure strat trap. And so when you come into something like that and you find it, it causes people to say, well, maybe we should re-examine strat traps, you know? When you find something like what's on the North Slope of Alaska, you know, it's a pure strat trap. And it's odd, I was trying to look at it this summer with Santos Energy, or last spring, but it's a pure strat trap. And so they exist out there, and when you find them, they're really big. And yeah, if you look at them, I mean, you know that, that's right. And yeah, and so they're really big, and but they're high risk, and they've always been high risk. And Amoco hated them, you know, they wanted structural traps when I was working there. But what really needs to happen is somebody from the University of Houston, somewhere, needs to put a student on looking at the viability, just the nature of the sealing facies of, say, you know, the West Siberia Basin traps, the North Slope Alaska traps, and, you know, the Cotton Valley. The Cotton Valley's right here, and it's a pure trap, right?
Yeah, but Alaska's kind of anomalous in that. Strat traps are quite viable, but that's because all the structures have pretty much been tested, except for animal.
Yeah. So strat traps are viable because all the structures have been tested.
Pretty much.
Why is that? That makes no sense to me then. It's like, strat traps are either viable or they're not viable, whether you've tested all the structural traps or not in a basin.
But
you know?
When I'm getting at it, it's hard to get people to drill these things.
Mm-hmm.
And when that's your option, you got a pipeline to fill like in Alaska, then it's more viable.
Then it's more economically viable, is what you're saying. Yeah. I mean, the situation you have in offshore Guyana right now is, you know, there's Lisa, and then there's sort of the string of pearls that's coming up through Suriname. But so far, it's been difficult to find. The Suriname guys have had difficulty in finding a similar scale of deep water systems and deep water traps that you have. They've got plenty of hydrocarbon out there. They've got some great source rocks. I mean, just as Paul and them's work has shown, you know, there's a lot of source rock out there and stuff. It's like, where's it going? Well, it's not, you know, another thing that would suggest that the seal is working in these shelf systems. There's beautiful bright amplitudes out there. And there's not big oil fields on shore like you would have in Venezuela. In Venezuela, everything was, you know, sliding up into the tar belt, right? But in Suriname, you don't have that on shore. The oils are different ages, you know. And so it just said it should be de-risked like everything else, I guess, you know. But yeah, but the other thing becomes you have other places to put your money in the world. I mean, India's got some great opportunities, you know. I had a visit with Eni this spring, and internally they were fighting on whether to put their money in Zohr or whether to put their money in these discoveries they were having in Indonesia, you know. It's like, that's why things in Kazakhstan, like Kashagan, are struggling, because, you know, there's only so much capital and there's opportunities around, right? So, yeah. So I wouldn't say that companies are going for more strat traps, but I would say that there are strat traps in the world that are enormous. And, you know, if someone is, you know, got the guts to go in there and sort of drill them and prove them off. But, yeah.
What you're talking about with respect to the size of the stratigraphic traps is true. There are a few supergiant strat traps in the world. But the thing that has not been looked at and talked about very much is really understanding the genesis and what makes a seal, because those kind of things have been drilled all over the place, and they're just productive in a few, and they're very large. And that, with all your data that you're talking about, you focus a lot on the sands. Look at the muds.
Yeah.
What's creating the seal in West Siberia? Those things are huge because they're stacked seaward prograding cladoforms.
Yeah.
Same is true in the North Slope. If you understand the seal on those cladoforms, you got a much better shot at selling your traps. But nobody's really looking that much at the muds.
Well, so from your mouth to God's ear, okay, and just to bring religion into it. And so one of the things, I had a student several years ago, and he looked at the size and shape and nature of seals. And we have all this data, the database that he put in there. And he read every conceivable paper on seals, because the first slide that he would show was how many papers were presented at AAPG and what was their topic. And something like 64% or 67% of the papers presented were on reservoir, and like 15% were on seal. And then if you look at studies, 75% of the things fail because of seal, and things seldom fail because of reservoir, right? And so his point being, we're not doing enough looking at sealing facies. And so the point I'm making with this is, someone needs to systematically look at paralic, muddy facies in places where they work, like Cotton Valley, like the stuff in North Slope, Alaska, like the stuff in the West Siberia Basin, to de-risk the sealing capacity of those type of paralic systems. I'm not so worried about the reservoir. The reservoirs are there. But if you're going to create the trap, you're going to have to seal them in the upward direction. You.
Me?
Yes, that would be you.
I think we're on the verge of a new phase of investigation into seals because of carbon capture.
Yeah.
I mean, that's such a critical part of carbon capture that's
Sure.
very poorly understood.
Yeah.
There's going to be a lot of research done on that.
Yeah, and it needs to be done. I mean, there were some nice precursors to looking at seals. Bill Allman with Chevron, did a lot of great work with seals. But Rich Gibson did a lot of good work with seals and stuff. But I agree with you. I thought you sounded like a man who had given it a lot of thought. But I think so. I didn't really think too much about dropping the ballast of bias against strat traps. It was more looking at this in terms of the quality of seismic data and the ability to de-risk these paralic sealing facies and stuff. And it certainly speaks to, if we're going to explore for them, we're going to have to de-risk the ability to seal hydrocarbons. And we may have to get to a financial point to where all the big things are found and we're going back to these traps and stuff.